Welcome to Digital Learning, Department of Collegiate Education. I am Professor Shobha. In this video, I am going to present you B.Sc first semester mathematics, matrices. In that, we are going to discuss about eigenvalues and eigenvectors of a square matrix and its properties. We would be able to learn the concepts of eigenvalues and eigenvectors, properties of eigenvalues and eigenvectors, working rule to find the eigenvalues and eigenvectors of a given matrix and apply it to find the same for the second order matrices. Students will be able to understand the concepts of eigenvalues and eigenvectors, properties of eigenvalues and eigenvectors, working rule to find the eigenvalues and eigenvectors of a given matrix and apply it to find the same for the second order matrices. Prerequisites are determinant of a matrix, definition of characteristic equation and characteristic polynomial, definition of a singular matrix. Characteristic matrix and characteristic equation. Let A be any n-row square matrix and lambda an indeterminate. The matrix A minus lambda I is called the characteristic matrix of A, where I is the unit matrix of order n. The determinant A minus lambda I, which is represented as in the determinant A11 minus lambda, A12 and so on so up to A1n, A21, A22 minus lambda and so on up to A2n, and further proceeding AN1, AN2 and so on up to ANN minus lambda, which are the elements of the determinant, which is a polynomial in lambda of degree n. This is called the characteristic polynomial of A. The equation A minus lambda I within the determinant is equal to 0 is called the characteristic equation. Let's define eigenvalues and eigenvectors. Eigenvalues. The equation within the determinant A minus lambda I is equal to 0 is called the characteristic equation of A, and the roots of this equation is called the characteristic root or the characteristic values. They are also called eigenvalues. If lambda is a characteristic root of the matrix A, then the determinant A minus lambda I is equal to 0 and the matrix A minus lambda I is singular. Therefore, there exists a non-zero x such that A minus lambda I multiplied with x is equal to 0 or Ax is equal to lambda x. Eigenvectors. Let A be a square matrix of order n. Suppose there exists a non-zero column matrix of order n cross 1 and a scalar lambda such that Ax is equal to lambda x, then x is called the eigenvector of A and lambda is called the corresponding eigenvalue of A. Relation between eigenvalues and eigenvectors. Let us see the first relation. Lambda is an eigenvalue of matrix A if and only if there exists a non-zero vector x such that Ax is equal to lambda x. Proof. Suppose lambda is an eigenvalue of A, then the determinant A minus lambda I is equal to 0 and the matrix A minus lambda I is singular. Therefore, the matrix equation A minus lambda I into x is equal to 0 possesses a non-zero solution. That is, there exists a non-zero vector x such that A minus lambda I into x is equal to 0 or Ax is equal to lambda x. Conversely, suppose there exists a non-zero vector x such that Ax is equal to lambda x. That is, A minus lambda I into x is equal to 0. Since the matrix equation A minus lambda I into x is equal to 0 possesses a non-zero solution, therefore the coefficient matrix A minus lambda I must be singular. That is, the determinant A minus lambda I is equal to 0. Hence, lambda is a characteristic root of the matrix A. Now let us see the second relation. For a given eigenvector, there corresponds only one eigenvalue. Let us see the proof. Let lambda 1 and lambda 2 be two eigenvalues corresponding to the same eigenvector x of A. Then Ax is equal to lambda 1x and Ax is equal to lambda 2x. This would yield us lambda 1x is equal to lambda 2x. That would imply lambda 1 minus lambda 2 into x is equal to 0. That implies lambda 1 is equal to lambda 2. That would prove our result. Let us see the third relation. If x is an eigenvector of the matrix A corresponding to the eigenvalue lambda, then k into x is also an eigenvector of A corresponding to the same eigenvalue lambda, where k is any non-zero scalar. Let us prove this. Suppose x is an eigenvector of A corresponding to the eigenvalue lambda. Then as x is not equal to 0 and Ax is equal to lambda x, if k is any non-zero scalar, then k into x is not equal to 0. Also, k into x is equal to k of a into x, and that would be equal to taking the value Ax is equal to lambda x. That would give us k into lambda x, and that would be equal to lambda of k into x. Now kx is a non-zero vector such that a into kx is equal to lambda into k into x. Hence kx is an eigenvector of A corresponding to the eigenvalue lambda. Also note that since k is not equal to 0, which is arbitrary, it follows that there are infinitely many eigenvectors corresponding to the eigenvalue. Let us see the fourth relation. Lambda is equal to 0 is an eigenvalue of a square matrix A if and only if A is singular. Suppose lambda is equal to 0 is an eigenvalue of A. Let x, which is not equal to 0, be a corresponding eigenvector, then A into x is equal to lambda x. As lambda is equal to 0, we would be getting which is equal to 0 into x, which is equal to 0. Thus the matrix equation Ax is equal to 0 holds for a non-zero x. Hence the determinant of A is equal to 0, that would imply A is singular. Conversely, suppose A is singular. That implies determinant of A is equal to 0. Then A into x is equal to 0 has a non-trivial solution. That is, there exists a non-zero x such that Ax is equal to 0. Since 0 is equal to 0 into x, this follows that Ax is equal to 0 into x. This shows that 0 is an eigenvalue of A. Now let us see the fifth relation. If lambda is an eigenvalue of a square matrix A with x as the corresponding eigenvector, then lambda square is an eigenvalue of A square. Let us prove this. Since x is an eigenvector corresponding to eigenvalue lambda of A, we have Ax is equal to lambda x. Multiplying A on both the sides will imply A square x is equal to lambda of Ax. That would imply A square x is equal to lambda of, here Ax is replaced by lambda x. That would imply A square x is equal to lambda square x. That means lambda square is the eigenvector of A square. Now let us prove that 1 over lambda is an eigenvalue of A inverse provided A is non-singular. Since A is non-singular, then lambda is not equal to 0. We have Ax is equal to lambda x. Multiply A inverse on both the sides. It gives us A inverse A into x is equal to lambda of A inverse x. A inverse A is a unit matrix into x is equal to lambda of A inverse x. Then that would imply x is equal to lambda of A inverse x. That is nothing but 1 over lambda into x is equal to A inverse x. Hence, 1 over lambda is an eigenvalue of A inverse with x as a corresponding eigenvector. Now, let us prove 1 over lambda, determinant of A, is an eigenvalue of adjoint A provided A is non-singular. By data, A is non-singular. That would imply A inverse exists. And A over A inverse would be given by 1 over determinant of A adjoint A. That would imply 1 over determinant of A adjoint A into x would be equal to 1 over lambda into x, where we are using the relation 2. Adjoint of A into x is equal to determinant of A over lambda into x. Hence, 1 over lambda into determinant of A is an eigenvalue of adjoint A with x as a corresponding eigenvector. Now let us see the working rule to find the eigenvalue and corresponding eigenvector of a square matrix A. First step, find the determinant of A minus lambda is equal to 0, which is the characteristic equation of matrix A. This equation will be of degree n in lambda if A is of order n. Next step, solve the characteristic equation. The roots of this equation are the eigenvalues, say lambda 1, lambda 2 and so on up to lambda n, which is not necessarily distinct. Step 3. To find the eigenvectors corresponding to the eigenvalue, we take x is not equal to 0 and write the matrix A minus lambda I into x is equal to 0. We set lambda is equal to lambda 1 in this matrix equation and solve it for x. Our solution x1 so obtained is eigenvectors corresponding to each eigenvalue lambda 1. Similarly, the eigenvector corresponding to the other distinct eigenvalues can be obtained. Now, let us learn to find the eigenvalues and eigenvectors of second order matrices. Let me consider a matrix A with the elements 4, 1, minus 1 and 2, which is a second order matrix. Start from forming a new matrix by subtracting lambda from the diagonal entries of the given matrix. The resultant matrix would be 4 minus lambda, 1 minus 1, 2 minus lambda. Find the determinant of the obtained matrix. The value of the determinant is lambda square minus 6 lambda plus 9. This is our characteristic polynomial. Solve the equation lambda square minus 6 lambda plus 9 is equal to 0. The roots of this equation are lambda 1 is equal to 3 and lambda 2 is also equal to 3. These are our eigenvalues. Now let us find eigenvectors. For the value of lambda is equal to 3, in the given matrix 4 minus lambda, 1 minus 1, 2 minus lambda, substitute the value of lambda to be equal to 3, which would be equal to 1, 1 minus 1 and minus 1. Perform row operations to obtain the row reduced echelon form of the matrix. That would result 1, 1, 0 and 0 by changing the row 2 as row 2 plus row 1. To solve the above matrix equation, Let us consider 1, 1, 0, 0 into x1, x2 is equal to 0 and 0. If we take x2 is equal to t, then x1 is equal to minus t and x2 is t. Therefore, our vectors would be minus t and t. Hence, our eigenvalues is 3 and eigenvector is minus 1 and 1. Now let us take one more second order matrix and find out the eigenvalues and eigenvectors. Start from forming a new matrix by subtracting lambda from the diagonal entries of the given matrix. Resultant matrix would be 5 minus lambda, 4, 1, 2 minus lambda. Find the determinant of the obtained matrix. The value would be lambda square minus 7 lambda plus 6. This is a characteristic polynomial. Solve the equation. We get the roots lambda 1 to be equal to 6 and lambda 2 is equal to 1. These are the eigenvalues. Next, let us find the eigenvectors for the eigenvalue lambda is equal to 6. In the matrix 5 minus lambda, 4, 1, 2 minus lambda, substitute lambda is equal to 6, resulting in the matrix minus 1, 4, 1, minus 4. Perform row operations to obtain the row reduced echelon form of the matrix, resulting in the matrix 1, minus 4, 0, 0. To solve the matrix equation, consider the matrix 1 minus 4 0 0 multiplied with the column matrix x1 x2 which is equal to the column matrix 0 0. If we take x2 is equal to t, then x1 would be equal to 4t. Hence our eigenvectors would be 4t, t. Now let us find the eigenvector for the eigenvalue lambda is equal to 1. Consider the matrix 5 minus lambda, 4, 1, 2 minus lambda. Put lambda is equal to 1, resulting in the matrix 4, 4, 1 and 1. Perform row operations to obtain row reduced echelon form of the matrix, resulting in the matrix 1 1 0 0. On interchanging R1 to R2 and performing row operations, R2 is equal to R2 minus 4R1. Now solve the matrix equation, that is 1 1 0 0 into the column matrix x1 x2 which is equal to the column matrix 0 and 0. If we take x2 is equal to t, then x1 is equal to minus t. Hence our vectors would be minus t and t. Hence the answer is for the eigenvalue 6 the eigenvector would be 4 and 1, and for eigenvalue 1 the eigenvector would be minus 1 and 1. Now let us learn to find eigenvalues and eigenvectors of the following second order matrix. So let me consider a matrix A with the elements 5, minus 1, 4 and 9. Start from forming a new matrix by subtracting lambda from the diagonal entries of the given matrix. The resultant matrix would be 5 minus lambda minus 1, 4, 9 minus lambda. Find the determinant of the obtained matrix. So determinant value would be lambda square minus 14 lambda plus 49. This is a characteristic polynomial. Solve the equation. The roots of this equation would be lambda 1 is equal to 7 and lambda 2 is equal to 7. These are the eigenvalues. Next, let us find eigenvectors corresponding to the eigenvalue lambda is equal to 7. In the matrix 5 minus lambda minus 1, 4 and 9 minus lambda, substitute the value of lambda is equal to 7. The resultant matrix would be minus 2, minus 1, 4 and 2. Perform row operations to obtain the row reduced echelon form of the matrix. The resultant matrix would be 1, 1 by 2, 0 and 0. On performing the row operations, row 2 is equal to row 2 plus 2 into row 1 and dividing row 1 by minus 2. Now solve the matrix equation 1 1 by 2 0 0 into the column matrix x1 x2 which is equal to the column matrix 0 0. If we take the value x2 is equal to t, then x1 would be equal to minus t by 2 and x2 is t. Therefore, our eigenvectors are minus t by 2 and t. Our eigenvalue is 7 and our eigenvector would be minus 1 by 2 and 1. Now let us find the eigenvalues and eigenvectors of the matrix A, which is equal to 1, 4, 3, 2. Start from forming a new matrix by subtracting lambda from the diagonal entries of the given matrix. The resultant matrix would be 1 minus lambda, 4, 3, 2 minus lambda. Find the determinant of the obtained matrix. The resultant matrix would be determinant of 1 minus lambda, 4, 3, 2 minus lambda, which would be equal to lambda square minus 3 lambda minus 10. This is a characteristic polynomial. Solve the equation lambda square minus 3 lambda plus 10 is equal to 0. The roots of the equation would be lambda 1 is equal to 5 and lambda 2 is equal to minus 2. These are the eigenvalues. Next, find the eigenvectors. For the eigenvalue lambda is equal to minus 5. Consider the matrix 1 minus lambda, 4, 3, 2 minus lambda. That would result after substituting lambda is equal to 5 minus 4, 4, 3 minus 1. Perform row operations to obtain the row reduced echelon form of the matrix. The matrix reduces to 1 minus 1, 0, 0. After applying the row operations. To solve the matrix equation, consider 1 minus 1 0 0 multiplied with the column matrix x1 x2, that is equal to the column matrix 0 0. If we take x2 is equal to t, then x1 is equal to t. Therefore, our eigenvectors would be t and t. Now let us find the eigenvector for the eigenvalue lambda is equal to minus 2. For the matrix 1 minus lambda, 4, 3, 2 minus lambda, substitute lambda is equal to minus 2. The resultant matrix would be 3, 4, 3, 4. Perform row operations to obtain the row reduced echelon form of the matrix. The resultant matrix would be 1, 4 by 3, 0, 0 on applying the row reduced echelon form. Now solve the matrix equation 1, 4 by 3, 0, 0 multiplied with the column matrix x1, x2 which is equal to the column matrix 0, 0. If we take x2 is equal to t, then x1 would be equal to minus 4 by 3 t. Therefore, our eigenvector would be minus 4 by 3 t and t. Hence, for the eigenvalue 5, the eigenvector would be 1 and 1. And for the eigenvalue minus 2, our eigenvector would be minus 4 by 3 and 1.